As with all network technologies, as spanning tree has been used over the years, it has evolved and it has enhanced. So what we're going to do now is take a look at the modern versions of spanning tree and some of the enhancements to the spanning tree process. First thing we'll start with is the spanning tree protocol port transitioning process, meaning why does it take so long for spanning tree to make a port go active? We'll then look at the initial enhancements to spanning tree that Cisco introduced, which is a per VLAN spanning tree instance. That was the initial one that was introduced a few years back, quite a few years back, to allow spanning tree to optimize your network. We'll then look at the newest and ultimate enhancement to spanning tree, which is known as the rapid spanning tree protocol, allowing your network to converge much faster. We'll also demonstrate some of the features that rapid spanning tree does, and we'll try the network failure that we did in the previous video with rapid spanning tree enabled and see how long it takes to fail over. Well, if you watched the previous video on spanning tree configuration, the original spanning tree, I think you realize that spanning tree has some problems. Well, it's not so much problems as it was just created a long time ago when things weren't expected to move so fast, when people could sit and enjoy a cup of coffee and shake your hand and look you in the eye and have a conversation. Not so nowadays. People just walk right by and how you doing? Okay, great, on their way they go. And it's the same way with networks. Networks are expected to converge like that, speed of light. If there's a problem, fix it. And fix it fast enough that nobody notices. So here's the problem with spanning tree. In its original creation, it went through two individual phases before it would actually start forwarding. And you'll notice this on every single Cisco switch. When you pull it out of the box and plug a device in, the little light above the port will stay orange, or that amber color, until about 30 seconds go by. The initial 15 seconds, the switch is going through the listening phase. And all it's doing during those 15 seconds is listening for BPDUs. See, here's the switch's thought process. It thinks if you plug a device in, that device could very well be another switch that could cause a loop in the network. It might have some redundant connections I don't know about yet. So it's going to wait 15 seconds listening to that port to see if it sees another switch's language, those BPDUs coming back through. If it does, and this port is not allowing BPDUs, it'll shut the port down. But if 15 seconds goes by and no BPDUs are received, it will transition to the learning phase. Now you might remember when we were doing the previous video on configuring spanning tree and I caused the failure, I shut down one of the ports, you could actually watch the port. When you do the show spanning tree command, it's showing you the port status going through this listening, or LIS is how it abbreviates it in the switch. It then transitions to learning, where it's trying to learn the MAC address that is on that port. See, if it makes the port active without knowing what MAC address is actually on that port, it's going to be very inefficient because it's going to have to start forwarding all the packets everywhere since it doesn't really know what is on that port. So it takes another 15 seconds to learn what MAC addresses are on there. 15 seconds is more than enough time for a PC or a server or whatever you have plugged in to send at least one packet with its source MAC address on there and allow the switch to populate the CAM table. So 30 seconds later, the port finally transitions to forwarding, and that's where the light changes from amber to green. Now that's going to cause a lot of problems in networks because, well, I'll talk about those in just a moment. I want to talk down here about the blocking phase. I call this the bonus timer. When you have a port, let's say that you have, let's do this. You've got a switch connected to another switch, connected to another switch, just like our topology we've been working with. And we'll say that these two are active right here. This is the blocked one. Well, as soon as you shut this down, the switch will implement a bonus timer. It's not really called that, I just call it that, where it waits about 20 seconds before it moves a block port into a listening phase. What it's waiting for is it wants to see if this is coming back online. Have you heard of a flapping interface? That's what it's waiting for. When that port goes off, meaning that it becomes disabled right here, well, spanning tree is going to go, whoa, well, before I transition everything over, let's just wait to see if it comes back online. I mean, that could be just an administrator unplugging the port to look at the cable and plugging it back in. And there's no need to upset the whole network if that port is just going to get plugged right back in. So you can see a bonus timer of up to 20 seconds. It could be a little less, but it won't go above 20. Will be implemented whenever there's a failure. So what does that mean? That means that if this fails, this port, before it will go active, will first go through its blocking timer down here, then transition to a listening state, then transition to a learning state to learn the MAC address, and then move on over to forwarding. That is up to 50 seconds of downtime per port before it can go active. These spanning tree delays cause two problems in our network. Number one is the problem with PCs. Modern PCs can boot faster than 30 seconds, meaning if you get the killer laptop or brand new desktop, it's going to be able to outboot the timer for spanning tree. So the port won't be active when the laptop is ready to go. Now it seems like a simple problem. It's like, well, wait 30 seconds before you surf the internet or something, right? Well, the problem is that when these PCs are booting up, they're sending out DHCP requests to get an IP address most of the time. So as they're sending out DHCP requests, they're not getting any reply. So in a business network, most people are using Windows XP Professional or Windows Vista Business, and you get the little press Control Delete to log on. The user goes to log on to their PC, username, type that in, password, type that in, and hit enter. And it says, sorry, the domain controller is not available, or I could not contact the domain controller because the computer doesn't have an IP address yet. Usually when the DHCP request fails, the computer will just kind of go in this standby state where it's going to still try and get an IP address, but it'll just wait 30 seconds or so to send out another request for an IP address. So the PCs are not able to log onto the network. The solution to that issue is port fast. And if you've played with Cisco switches before, chances are you've heard of port fast. This is a tool that essentially disables spanning tree. It turns it off on the port. And I went ahead and we'll type this in on some live switches, but I wanted to show you the warning message that you get when you type this command underneath the port. It's like a little essay that it gives you in the iOS. It says, warning, it should not be enabled on, or should be enabled only on ports connected to a single host, connecting hubs, concentrators, switches, bridges, etc. to this interface. When port fast is enabled, can cause temporary bridging loops. Use with caution. So that's the warning to you, is that you are turning off spanning tree on this port. So the port will go active right away as soon as you plug in the device, but that could cause loops in the network. The other issue that spanning tree causes is that it has problems with uplink ports, meaning ports connecting to other switches. 50 seconds of downtime in any network can cause big problems. There's a lot that can go wrong during that. The solution to that issue is the new version of spanning tree, Rapid Spanning Tree. Now, before we get into what Rapid Spanning Tree is all about, let's first talk about the initial enhancement that Cisco made to the normal spanning tree protocol. What Cisco created was a different version called PVST. That's Per VLAN Spanning Tree Plus. That's Cisco's little enhancement to it to say Per VLAN Spanning Tree by default when they first created it was only supported on Cisco switches. Now it's become essentially an industry standard that anybody can do. But what Cisco's initial enhancement did to Spanning Tree is allow you to run an instance of Spanning Tree per VLAN. As if spanning tree wasn't confusing enough already, there's going to be many instances of spanning tree running. Here's the idea behind it. Down here I have our little topology that we're using in our network with 3 switches. Now in our network diagram, this one right here became the root bridge. Now ignore my little notes over here for just a moment. Just imagine that is the root bridge for everybody. What will happen is these will be the active links that are used between the 2 switches. This one ends up being disabled until it's needed because of a network failure. So what that means is everybody's going through the root to communicate, as it should be, right? But if you think about it, you just disabled a potentially useful link in your network, meaning this is going to be completely unused, but man, it would be handy if we could use it for at least some of our network traffic. That's what per VLAN spanning tree is all about. What we can do is have separate spanning tree topologies for each VLAN that we're creating. For example, you can see my notes. It allows different route bridges per VLAN. Essentially, I could say this top switch is the route for VLAN 10 traffic. And what that means is for VLAN 10, these are going to be the active links, and those will be used, and no VLAN 10 traffic will ever cross this link over here. But I could set a separate route, thus the per VLAN spanning tree, for other VLANs. So I could say the route for VLAN 20 is this switch right here, and if we did that, the new topology looks like this. These are the, hang on, let me do this. These are the active ports for VLAN 20, and this one ends up becoming disabled, so VLAN 20 will never cross this link. What you're doing is almost a manual system of load balancing, so that VLAN 20 will start using this link that was typically unused before and still is unused. Phone! And VLAN 10 will be using this link, which is completely unused for VLAN 20. So now you've got 100 megabits per second of dedicated bandwidth, on that line for VLAN 20, and you've got 100 megabits per second of dedicated bandwidth on that line for VLAN 10. You could do that for all the VLANs in your network. Now you can start seeing why in large networks, man, can this be complex. You essentially can draw a separate diagram for every single VLAN that you could have. I mean, if you were drawing this out, I could say, okay, well, this is my VLAN 10 topology and highlight my active links for VLAN 10. I could then draw another picture over here. You know, these are my VLAN 20 topology where we have active links right here, and this one's disabled. And you could create a separate network diagram for every VLAN that you have. As a matter of fact, let me show you what this looks like on the live switches. I'll bring up my connection to switch 1. And there we are. Now, if you remember from the previous video when I did the initial spanning tree configuration, the command was show spanning tree, and you just hit enter. And during that video, I have a confession to make. I wasn't showing you the whole story. Whenever I saw this more symbol right there, I just hit Q on the keyboard and say, see, look, this is how spanning tree's working. That's because in this video, I want to show you the rest of it. I'll hit the show spanning tree, and you can see VLAN 1, we have the root ID. This is the root, this is switch 1, and so on. But watch what happens if I hit space. Look at this. It says for VLAN 10, I am not the root. There's another root out there that is, my guess is that it's switch 2, because that was the original root. Because when we were adjusting the priority, we said that, or the command we used was spanning tree, and then I would type in VLAN 1, because I said we're using VLAN 1 everywhere, which adjusted the priority for this as the root bridge on VLAN 1, but didn't adjust it for VLAN 10 and VLAN 20 and 30 and all these other ones that we're using. Look at this. VLAN 1, VLAN 10, that's I think our sales VLAN, and you can see all the information there. VLAN 20, all the information there. VLAN 30, all the information right there. You can see it's the only VLAN that this is a root on is VLAN 1, and that's all the VLANs we have. So by default, the Cisco switch is running per VLAN spanning tree plus. So it's running an instance on every VLAN. So if you want to set this to be the root bridge on all the VLANs, you need to type in spanning tree VLAN, and you can see question mark. I can type in a range of VLANs. I was just typing in 1, but we could also say 1, 10, 20, 30, and then do a question mark and do, this will be the root primary for all of them. So now this is the true root for all the active VLANs that we have. If I do a show spanning tree again, now you can see VLAN 1, this bridge is the root. VLAN 10, this bridge is the root. VLAN 20, this bridge is the root, and so on and so forth. So that is how you can set the switch to be the root for different VLANs, and that is a nice enhancement because we can then manually set up different routes so that we use a load balancing characteristics. Some VLANs will use some links for their traffic, other VLANs will use other links. The only way you're going to be able to make this work efficiently is to have an accurate up-to-date network diagram of your switch connections so that you're going to be able to identify which switch ports get blocked, which ones are active. And that's one of the skills that you'll have to master is based on the root bridge in the network, wherever the root is, which ports are actively being used. Now, I say you have to master that, not only for the real world, because you're going to be setting this up, but be prepared when you get to certification exams to see network diagrams, to see where a root bridge is, to see the speeds of all the links, and to say, well, these ports are going to be active, this one won't be active, so that'll be blocked. And I mean, seriously, the exams have been enhanced in a major way where you're going to be able to have a full topology identifying each one of those active links. It's pretty powerful. So per VLAN spanning tree is an enhancement, but it's still the same old spanning tree engine, just on multiple VLANs. So the people have spoken. The network industry has progressed and needs more speed, and our signs are saying, end spanning tree, 50 seconds, we can't have this, and all the revolt. So the industry giants that create all the standards responded with a new standard, 802.1w, or the common name is Rapid Spanning Tree Protocol. What it is an enhanced version of spanning tree that is much more proactive than the previous. Now let me define proactive. In the spanning tree protocol, when it finds all the active links and says, okay, these are our active links, let's block these other ones, it essentially forgets about them, meaning they're blocked, they're not causing a loop, we're active, we're working along. So when the active link fails, spanning tree goes into a reactive state, meaning, oh no, primary link's lost. Now what do we do? Start looking at all these other ports to try and discover a backup path. Rapid spanning tree, on the other hand, is proactive in the sense that once it finds its active ports, it sees the backup ports as just that, backup. Meaning rapid spanning tree remembers. If you've got this switch topology here of our 3 switches, and it says these top 2 are going to be our primary ports, and this one will be blocked, rapid spanning tree remembers, oh yeah, that can be a good backup port. I mean, it sounds so simple, but that's all it really does. Spanning tree forgets about it, so if one of these dies, it has to rediscover where this link goes. So with rapid spanning tree, you get redefined port roles. Instead of saying it's just blocked, it will actually see it as an alternate port. The catch of rapid spanning tree, it's kind of one of those things where people think, oh, that's a no-brainer, let's use rapid spanning tree. The catch with rapid spanning tree is it's a fairly new standard. And when I say new, I mean, the standard, now I'm just guesstimating here, but the standard came out probably 5 years ago from now, which is 2007, 2008 timeframe. So I'm talking at the end of the year, so I'm sure this recording will bleed over into the 2008. So, around 2003, but there are still 100 megabit per second switches out there that work perfectly fine that, are 5 years old and people are still using them. Likewise, just because a standard comes out 5, 6 years ago doesn't mean everybody's like, oh, implement that standard. So switches really only started, everybody supporting rapid spanning tree within the last 3 to 4 years. So in order to have rapid spanning tree work, you have to have it running everywhere, which means that there's some major network upgrades going on. If there's one switch in the network still running spanning tree, it will cause everybody to slow down because they created rapid spanning tree to be backwards compatible. So if it sees an old spanning tree switch, it's going to say, well, let's match those timers and slow ourselves down so that we can work with this network. So in order to run rapid spanning tree truly, it must be everywhere. I jumped a little bit ahead of myself in drawing that little switch network on the previous slide, but this is the official how our STP does what it does. The main difference is, just like spanning tree, the old version, it has root ports. It has designated ports, meaning one per link, it will have a designated port. But instead of saying it has blocked ports, it sees those as alternate ports. That's the new port type. So instead of just saying, you're blocked, you're done, it sees this as an alternate should one of the root ports fail in the network, and it can use that quickly as an alternate link. So what I want to do to wrap this video up is demonstrate the difference in speed when you compare rapid spanning tree versus spanning tree, and also show you how to turn it all on. So here's our network diagram that we've been using to test spanning tree. Again, what we've done is installed the redundant link connection right here on 0/24 on both of these switches. The switch 1 up top is our root bridge for all VLANs. And by the way, Cisco does implement per VLAN rapid spanning tree. So they took their enhancement and moved it into a per VLAN level for rapid spanning tree. So let's set it up. And again, we still have these two hosts that can do our ping testing. We've got switch 1 that we're on right now. And to start rapid spanning tree, it's just one command, piece of cake. Global config mode, you type in spanning tree mode, and then you choose which mode you want. By default, every Cisco switch runs per VLAN spanning tree, but they also support multiple spanning tree, which is the old version, the really old version, meaning you can run one instance of spanning tree per all VLANs before Cisco enhanced it. They still support that version, because if you use per VLAN spanning tree and have a ton of VLANs, it can actually cause a lot more processor cycles than Cisco originally intended. So you might just say, well, I want to go back to multiple spanning tree mode where you have one spanning tree instance for multiple VLANs, and that way you don't eat up all the resources on your switch. But what we're doing right now is converting to rapid spanning tree, and so you just type in spanning tree mode rapid, or rapid PVST is the one Cisco supports. Now, in order for that to work, you notice it kind of bounces the VLAN interface. In order for that to work, we have to turn that on all our switches, because otherwise the timers won't increase. They'll detect spanning tree still running in the network. So we'll say spanning tree mode rapid on switch 2. Jump over to switch 3, spanning tree mode rapid. So now we're running rapid per VLAN spanning tree on all of our switches. It'll take a second for them to converge. I'll just do a show spanning tree one more time, and you can see spanning tree enabled. The protocol is rapid spanning tree protocol. This is still the root bridge. All the other spanning tree concepts still apply. It's just now we have let's go to switch 3. Show spanning tree, you see that we have this alternate port that is labeled as that role, and it's actually being used as an alternate port. It's still blocked, sure, because we still have to stop the loops, but we have now this active alternate port. So this can still be combined with port fast to allow ports to transition quickly. So with that in place, let's do this. I'm going to open a command prompt on my computer. And once again, if we go back to the network diagram, I'm sitting on this computer right here, the 1.50, and I'm going to issue a continual ping over here to this PC, 1.20. I'm going to introduce, the same network failure that we had previously. I'll ping 192.168.1.20-T. Keep that thing going. We can see that the ping is being successful. I'll squinch this one up at the top so we can watch what happens as the ping messages fail. Let me squish this one down right here. I'm going to jump over to switch number 1, which, since this is the root for all VLANs, these are the active links that are going. This one down here is blocked. So I'm going to cause the same failure and shut down fast Ethernet 0/12, and let's see how long it takes the PC to recover. So let me bring up my continual ping going on. Jump over to switch 1, and I'll go into interface fast Ethernet 0/12, and you can see this ping is still going. Every now and then you get an equal sign that you can watch, and I'll type in shutdown. So we have the interface went down, we have request timeout. Supposed to be faster than that. Hang on. I'm like, okay, we're failing. Let me do a show spanning tree. We've got rapid spanning tree is enabled. Let me hop over to switch 3. Wow, we just okay, wow, yeah, that was rapid right there. That wasn't rapid at all. So let me do a show spanning tree on switch 3. Looks like it's got the new root port that it's using. Everything's in a forwarding state. Sometimes if you cause the failure too quickly, after converting to a rapid spanning tree, it hasn't actually detected the whole network running rapid spanning tree. So let's try this again. Hang on. Let me go back to switch 1, interface fast Ethernet 0/12, and I'll do a no shutdown. Power that active port back on. Now, if you remember in the previous video, the no shutdown caused an immediate failure. And in the same sense here, we're going to get an immediate failure. Okay, this isn't working like it's supposed to. Let's take a look. I'm going to jump over to switch 3, do a show spanning tree. Let's take a look. It looks like we've got the designated ports that have gone into a learning state. You know what? You know what I just realized? We have not turned on port fast. And when I say we, I mean I haven't. So the hosts that are pinging each other, as soon as the active link goes down, you can see that I have fast Ethernet 0/4 and 8. Those are actual hosts that are plugged into that. You can notice what mode they were in. They were in the learning mode. So I still need to turn on port fast. I didn't even think of that in order for this to take effect. So as of right now, I have the original topology restored. We have a blocking port. Let me go under on switch 2, fast Ethernet 0/8, and I'll type in spanning tree port fast. And there's the message. I showed you that at the beginning of this video, saying, you know, port fast is not to be enabled on non-switch ports. So I'll go under the fast Ethernet 0/4. That's my router connection. Also turn that on port fast. And then let me hop over to switch 2. If I do a show IP interface brief, I can see that I still have that PC plugged into fast Ethernet 0/8 right there. So global config, spanning tree, port fast. There's our little message. Let me just jump back here and mention what's happening. Whenever there's a failure in spanning tree and we cause this catastrophic failure, it will reset the ports. Now, the ports that are port fast don't even notice that because they'll instantly go to a forwarding state. I forgot to turn on port fast on our host ports and also the router connection. That's our fast Ethernet 0/4. That should be down here. So that the router, since the router's an active host, it's going to go to an immediate forwarding state as well. So let's try that one more time. Bring up my prompt. Bring up my ping message. Now I'm going to hop back up to switch 1. I'm going to do the same thing. I'm going to kill the fast Ethernet 0/12, so the redundant link 0/24 has to be used. Interface fast Ethernet 0/12. Let me get my ping messages going back up. All right, they're pinging. I'm going to do a shutdown. Did you see that? Oh, nope, you didn't. The ping is still going. There was no failure. That's what I expected with rapid spanning tree. Now I'm going to jump back over to switch 3 and do a show spanning tree, and you can see that the fast Ethernet 0/24 immediately transitioned over. That's the spanning tree effect I was looking for, because as soon as it goes into the failure state, it says, oh, that's my alternate port. Let's immediately click over. Now, when the original link gets restored, usually there's a moment of failover. Let's see if it happens now. I'm going to do a no shutdown, bring that original link back online. You can see the pings are still going up top. There we go. Fast Ethernet 0/12 is changed up. There we go. We have one dropped ping. That's the typical failover time for rapid spanning tree. The initial failure is immediate, meaning it's got the alternate port, click, it's shifted right back over. Then the consequent failures after that will if we're switching back to the primary, will cause just a single instance, 1 or 2 seconds of a network outage, and that was enough to drop a ping packet. So overall, rapid spanning tree is much faster than spanning tree. See, and we demonstrated both in one demonstration. Spanning tree, the original, you saw the 30-second timeout, and then rapid spanning tree after I enabled port fast on our PC ports to take over the network and recover quickly. So Rapid Spanning Tree is designed to have almost an instantaneous failover in our network environments so that when network failures do happen, hopefully no one will even notice. So the enhancements to Spanning Tree, while we walked through this, we saw the normal Spanning Tree port transition process, which is the listening, learning, followed by the forwarding state, which causes a typical 30 seconds network outage or network uptime while it's waiting to get to forwarding. That causes problems because PCs can boot faster than that and networks need to converge faster than that. So Cisco's initial enhancement to Spanning Tree was per VLAN Spanning Tree, which allows you to run one instance per VLAN having different root bridges in the network and setting up a type of manual load balancing. Finally, the ultimate enhancement to Spanning Tree is that 802.1w or Rapid Spanning Tree, which you just saw, is a near instantaneous failover. I hope this has been informative for you, and I'd like to thank you for viewing.